So I'm assuming you can see my screen. Is my screen visible?
Yes, sir.
Yes, sir.
Okay, thank you. Thank you. All right, so let's start. So in the last class, we solved this math. So I believe this was a very simple math. In some of the sections, some of you had a little bit confusions regarding radian and degrees as when to convert and when not to convert. So it is actually up to you. If you have a very clear idea of in which formulas by interchanging degree and radian the result will be affected, you can switch in between as long as you have a clear idea. But if I talk specifically about this particular math, that is example 11.4, okay, I'm talking about this specific math, then even if you keep your angles in degrees, okay, not in radians, if you keep them in degrees, there will be no problem throughout. Okay, you will get the exact same answers. However, in some maths, like some of the examples that we solved previously, there was a term omega or angular velocity. Most of the cases, those velocities are given in radian per second. So in those cases, whenever in an equation you have your omega and there is a corresponding degrees, then you must convert them to radian because all of them has to match. Otherwise, you have to convert that radian per second to degree per second, which is a little bit complicated. So bottom line is, if you want to avoid all these confusions altogether, then it is always better that whatever angle you get, just convert that to radian and then use in radian mode. Of course, your calculator must also be in radian mode. Okay. So that is the conclusion. So we solve this math. Whenever you solve this type of maths in your exam, make sure you provide a figure like this, because this figure clearly represents whatever answers you have achieved. Yeah. So this is your table. As some of you already know that the entire solution is possible using a calculator. So if you want, you can use the calculator, but don't take the answer right away. At least take your initial value slightly higher or lower than the actual value so that you need less number of iterations to converge. Okay, that's fine. But do not directly write the answer using your calculator. So we start from here today. So previously we saw the application of equal area criteria. And what we did, we saw how our equal area criteria is applied if we have a change in the input side, that is mechanical input power. So if there is a change in mechanical input power, then we saw how equal area criteria is applied and what was the significance of that equal area criteria. So now we'll change our application a little bit. That is, we'll apply a three-phase fault at one end of the transmission line. Now this fault, instead of happening at one end, it might happen at the middle as well. So that section will take next. Just a second. Okay, as I was saying that now the fault is over here, but instead of there, your fault might happen over here as well. Okay? So this scenario will take next. Again, instead of happening in this particular end, your fault might happen at this particular end as well. So, but this will be kind of identical. So if you can analyze your system using the fault at this particular node, you can also analyze the fault at this particular node. Okay, and assuming the fault over here does not make a significant difference because you can assume since both of the lines are parallel, so you can do the calculation. If you understand for one position, you can easily go for either this position or this position. The analysis will be very similar and quite clear. All right. So now we'll see what happens if there is a fault at specific end of our transmission line. In this case, again, we'll have some assumptions. So what is the first assumption? That is, in the input side, we will assume that there is no change. Previously, our assumption was that our PM was increased, step increase, but our PM was increased from the input side, mechanical input power. But now we will assume that throughout our analysis, my PM will be constant. That is, there will be no change from the input side. So this is done. And the machine is operating steadily with a power angle delta naught. That is fine. I mean, every time we start, we have to assume that the machine is operating at a steady state stability. And from there, we start applying some sort of disturbance and try to see how the system behaves. All right, so this is the initial condition. So this is the same SMIB that we had been dealing so far. So nothing to discuss about this SMIB. Now we apply a temporary three-phase bolted fault. Okay, so there are, it is highlighted in red color. So there are a few things to discuss on this. So first of all comes the term temporary. So what do we understand when we say temporary? That means we assume that the fault will last maybe at best for a few milliseconds. So what does it mean? It might happen that you have a lightning strike. Okay. So if there is a lightning strike, your fault will only be active as long as this lightning is present, which is present maybe for a few microseconds, not even millisecond. Okay. So once this lightning disappears, your fault also disappears. What can be the other possible scenarios? You might happen that you have got a tree over here. Okay. You might have a tree over here, and say because of a big storm or huge amount of wind, your tree starts swinging. So while swinging, while it is coming on this side, say somehow it is touching this wire. So if it is touching this wire, it is getting a shorted path to the ground via the tree. Let us assume that the tree is wet. Okay. So it is getting a shorted path via the wind. But again, the tree is swinging, right? So as soon as the tree comes over here, my fault is removed. So there may be many other scenarios like this. But the bottom line is, whatever is the scenario, in every case, your fault will be persistent only for a few milliseconds, and then the fault will disappear. Okay, that is the first assumption. A temporary three-phase fault. What can be a more severe fault than a temporary fault? It can be if the fault is permanent. That is, the tree fell on the transmission line and somehow the transmission line is torn apart. Okay, so that is a permanent fault. Nothing can be done until and unless you replace those transmission lines. Okay, so we are not dealing with those things. Those require physical activity, and those are not a huge part of our analysis, because if your transmission line is broken, there is nothing that you can do just from your controller side. So someone has to go over there, amend those lines, then again the system will come back on. So we're not considering that. We will consider the temporary fault. So that is the first thing. What is the temporary fault? Next comes a three-phase fault. So what does it mean when we say with three-phase fault? That means we assume that these lines are carrying three-phase currents. So when we say that these lines are carrying three-phase currents, that means there are three separate lines carrying the three separate phases. So if there is a three-phase fault, that means all of the three lines are suddenly grounded for a few milliseconds. Okay. What does it mean if we say a single phase fault? That means out of the three phases, only one phase is suddenly grounded. The other two phases are still active. Now, if I ask you a simple question, which one is more severe, three-phase fault or single-phase fault? What will be your answer? So like I said, if you are in the class, you have to respond. Okay, otherwise we are free to leave. So at least try. Which one is more severe? What do you think? Three-phase fault or single-phase fault?
So
Maybe three-phase fault.
Again?
So three-phase fault.
Okay, why three-phase fault is more severe than single-phase fault?
I don't know, sir. I just guessed.
Okay, fine. That's fine. But the second question was very obvious. Even if you had said single phase is more severe than three phase, I would have asked the same question. So the answer is correct. Three phase fault is actually more severe than single phase fault. Can anyone try and give the explanation why three phase fault is more severe than single phase fault? Just try and think. What do you understand when we say severe? First of all, try to understand this portion. Okay. Remember, these things are, again, these are important things. These are not written on the slide. That does not mean these are not going to come in the exam. Okay. Whatever I discuss, everything is important. Okay. So now come. When we say severe, what does we mean when we say more severe, less severe fault? How do we determine the severity? What is the parameter?
difficult to solve the
Mm-hmm.
difficult to solve the problem.
difficult to solve the problem? Actually, no. That is more complicated problem or like that. But when we say severity of a fault in transmission line, we actually do not go with the complexity of the fault. There is another parameter that determines which fault is more severe, which fault is less severe. First of all, we need to know what is that parameter. Any other guesses?
So the deviation in voltage and phase.
The deviation in voltage and phase. No, but again, that is an important parameter, but that is not the determining parameter. Any other thing? Any other guess? No, okay, fine. Let me give you the answer. The answer is it depends on the fault current. Okay. So if the fault current is more, we say that the fault is more severe. If the fault current is less, we say the fault is less severe. So now, since you know that the fault current is the determining factor, so now tell me how three-phase fault is more severe than a single-phase fault.
So the fault current is more severe in three-phase.
স্যার ফল্ট হলে তাহলে তিনটা তার দিয়ে কারেন্ট যাবে তো বেশি কারেন্ট যাবে
আবার I missed it. Say again.
বেসিক ফল্ট মানে হচ্ছে তিনটা তার দিয়ে কারেন্ট অনেক বেশি যাচ্ছে ফল্ট করে আর সিঙ্গেল পেস মনে হচ্ছে একটা সাইড দিয়ে শুধু কারেন্ট যাচ্ছে আর বাকি দুটো দিয়ে ফল্ট কারেন্ট যাচ্ছে
Yeah, I mean almost there. Yeah, your explanation is almost there. So you see that when you have three wires carrying current, so you have got current carrying over here, this wire, this wire. So these are say three phases which are carrying the current. If you have a single phase fault, that means one of the phases is suddenly grounded. So the other two phases are remaining intact. So whatever current was going through the other two phases, they will remain as it is. Only the current through one of the phases will be grounded, right? So now, if all these three are grounded, then definitely the fault current will be the maximum when all the three phases are grounded, isn't it? Right?
ইয়েস স্যার
Yeah. So this is the reason why a three-phase fault is more severe than a single-phase fault. Okay, make sure that the explanation is correct, okay? Because if I ask you in the exam, you also have to give your explanation. So make sure you understand these things. Okay, so we are done with temporary. We are done with three-phase. The next thing is a bolted fault. So what does it mean when we say that there is a bolted fault? Bolted fault means the fault is happening over here at point F. So point F to the ground, okay, let's assume this is the ground. So you will have a path to the ground. If there is no resistance, okay, or impedance, if there is no impedance from the fault point to the ground, then we say it is a bolted fault. If for some reason there is some kind of resistance or impedance between the fault point and the ground, then it is not a bolted fault. It will only be a bolted fault if it has a short circuit path from the point of fault to the ground. So is it understood what is the meaning of a bolted fault?
ইয়েস স্যার
Okay, so the same question again. Which one is more severe, bolted fault or not bolted fault? Which one is more severe?
Voltage fault.
Louder.
The voltage fault. Because
আমি শুনি না কেন তোমাদের কথা?
It's a bolted fault.
Yeah, now I can hear. Yeah, bolted fault. So why is bolted fault more severe than a not bolted fault?
Because the fault current will be higher because there is no resistance.
No impedance, exactly. Because the fault current will be higher as there is no impedance. All right. So now we know all these things. So what is the meaning of a temporary three-phase bolted fault occurs at the, let's say, sending end of the line at bus point 1. Okay, so we know up to this. So what will happen? So first of all, the power transmitted to the infinite bus will be 0. So how we'll explain all these things? Okay, let's not get confused. So we'll explain all these things. The power angle curve corresponds to the horizontal axis. Again, we'll explain this. The machine accelerates, we'll see how speed, stored kinetic energy, and rotor angle increases. So all these things we will explain with the help of equal area criteria. Okay, so what is the last assumption? When the fault is cleared, both the lines are assumed to be intact. That means, as we said initially, that there will be a tree. So it is coming, it is getting a shorted path, but as soon as the tree moves away, my current is going as it is supposed to go via the lines. Okay, so that means when the fault is cleared, both the lines are assumed to be intact. Okay. So any question over here? Okay. So if there are no question, let's move forward. So whenever we have fault, we need to do the analysis in 3 steps. First of all, you have to check what is your network before the fault. Then you have to check what is your network during the fault. And then you have to check what is the network after the fault. Okay. So these are the 3 stages which you have to analyze whenever you have some kinds of fault. Okay. So this is my SMIB, nothing complicated over there. This is the corresponding circuit. This is known as per phase equivalent circuit. Okay. This is known as, since it is a, I mean, again, a 3-phase fault is a balanced fault. Okay. Because whatever is happening is equally applicable for all the 3 phases. So if you go for per phase equivalent circuit, you will get the exact same result. But if it is a single line fault or single phase fault, then you have to specify in which particular phase you are having the fault and analyze accordingly. But since it is a 3-phase fault, it is an equivalent fault. So we can go for per phase equivalent representation. So this is the per phase equivalent representation. We can see this xd dash is given over here. This xt is taken care over here. X12, the impedance of both the lines over here, we are assuming completely, I mean, there is no resistive part, okay? Only inductive in nature. So we are taking the inductance in X12, both are similar. And then this is the infinite bus. So we get, and this one, all of you already know what is the X equivalent. So if you combine all of them, then whatever equivalent impedance you get, that is your X equivalent before fault. Okay. So if you calculate your power, it will be, you know, E V, I mean, of course, there will be magnitude. So E dash V dash divided by X equivalent before fault. Any question over here? Okay. Now let's modify this one. Okay. And let's see what happens. If there is a fault, the fault is happening at this particular point, right? At particular point F. Over here, the fault is happening. So if the fault is happening over here, what will happen? This transmission line will become inactive and there will be a shorted path from here to the ground. Do we agree? Do we agree with
sir.
this configuration? Okay. So my xd dash will remain as it is. There will be no change at xd dash. There will be no change at xt dash. Over here is this will be some function of x12 or x. I mean, something we are not that interested in. I'll explain why we're not that interested. So now let's see what will happen. Say first of all, current will come over here, I1. Now it has got 2 paths. Say this is I2 and this is another path, I3. So according to current division rule, I can write that I1 is equal to I2 plus I3. Is it okay up to this? Applying KCL, can I write this thing?
Yes, sir.
All of you agree?
Yes, sir.
Okay. Now one simple question. Tell me what will be the relationship between I2 and I3? What will be the relationship between I2 and I3? Or any sort of, I mean, if I say someone has to be greater or less, I mean, what is the sort of
I3 is greater than I2.
I3 is greater than I2? Do all of us agree? Do we agree? Or someone has a different opinion? Come on, these are your simple basic circuits. Okay, you should know these things. Either yes sir, no sir, something. At least say something. So all of you agree that I3 will be greater than I2.
Yes, sir.
Okay. If I ask you, how much greater? I mean, just roughly, how much times the magnitude will differ? 10 times, 100 times, 2 times, 3 times, or almost comparable but greater? What will be your answer? How is I3 compared to I2? I3 is larger than I2. Fine, I accept that. But how much larger?
It should be very much larger than I2. Almost all the
Mhm.
current will go through that line. Sir,
Say
almost
again.
all the current will go. Sir, almost all the current will go through the that shorted line. So I2 will be much
Almost
better than
all the currents will go through the shorted line. So what will be the value of I2?
so 0, 0.
Definitely it will be 0. This is the thing I had been expecting for a very long time. I mean, why did you take so long to answer this thing? If you have a circuit like this, okay, if you have a circuit like this is your I1, this is your I2, this is your I3. If your current gets a shorted path, will there be any current going through I3? Will there be any current? Basic circuit from your 1-1 first semester. So if your current gets a shorted path, will there be any current going through the resistive path or the inductive path? Will there be any current?
No, sir.
Come on. So this thing should have been very clear, right? So that means this relationship can simply be written as your I1 is equal to your I3 and I2 is 0. Clear up to this?
Yes, sir.
Okay. So if no current is going through your terminal voltage, what will be your PE? Say, let's say this is 2. What will be your power delivered to the terminal voltage during fault?
0. It should be 0. Because
Definitely. So it will be 0. So this was our first point over here. This is the first point, that is power transmitted to the infinite bus is 0. So we understood why it is 0. Everyone clear? Okay.
yes, sir.
So this exact same thing is actually written over here. I mean, not written, just drawn over here. The explanation I already gave you. So you have got a shorted path. So the entire current will go through this shorted path. There will be no current going through the other path. So definitely the power transmitted will be exactly equal to 0. Getting back over here. So how will your network look like after fault? Can anyone tell me? How will your network look like after fault? Come on, no one. Kyun parba na?
Sir, there will be only E dash, XD dash, and XT, and the remaining they will be in the series.
There will only be, come again, XD dash, XT and
E prime.
হ্যাঁ বুঝি নাই।
Sir, E prime, XD dash, or XT factor should.
So these things will not be there. I'm talking about
Sorry,
after fault. I'm talking about after fault. How will your network look like after fault?
Sir, E dash, XF, X12, and the terminal voltage.
So what will be the change?
Sir, X12 will the line that was shorted will no longer be in account.
Why?
Sir, due to the short, it will be flipped off.
I'm talking about after fault. During the fault, it will be shorted. That is fine. During the fault, it will be shorted. But what will happen after fault? We said that the fault will last for a few milliseconds, right? A tree might touch the transmission line. So your network will get a shorted line to the ground for a few milliseconds. Once the tree moves away, both the transmission lines will remain intact, right? The last
Sir,
point,
it will be the
when the
same.
fault is
It will
cleared,
be
both the
the
lines are assumed to be intact. In that case, what will be the network after fault?
So it will be the same as the before fault.
Exactly. It will be the exact same network before fault. Okay. So the network before fault and network after fault, there will be no change at all. The only change will be during fault. So if I go for after fault, you see there is exactly no difference at all. Is it clear why there is no difference between the network before and after fault? Understood?
Yes, sir.
All right. If we understood so far, now we will apply the equal area criteria and we'll try to see what is happening. So let's draw them. We always go for the PE and delta power angle curve, right? So my curve will look something like okay, let's fine. Okay. So initially we were we need to work on a fixed operating point. So let's say that initially we are operating at this particular point where my PM naught is equal to my PE naught. I'm operating at point A. And let's say this is my delta naught. Any question until this point? This is my 0. Any question until this point? Okay. So the figure that I drew, tell me, this is before fault, after fault, or during fault?
Sir, before fault.
Before fault. Okay. We all know the formula for PE is P max sine of delta. That is how we got this curve. Okay. So now let us try and understand what will happen when there is a fault. So when there is a fault, what happens to your electrical power during fault? During fault, what happens to your electrical power?
So it becomes 0.
It becomes 0. So can I say your operating point will come, let's say this is B. So can I say that your operating point will come to B? Can I say that?
Yes, sir.
Okay. So initially my operating point was at A. That was before fault. During the fault, we just saw that the power transmitted to the infinite bus will be 0. So from there, we see that the 0 line is along the horizontal line. So we can say that my operating point will come towards B. Okay. Now tell me, at B, what is the relationship between your PM and PE? What is the relationship between PM and PE at point B?
PM greater than PE.
Very good. PM greater than PE because PM is fixed. We are not going to change PM in this analysis. Our PM will remain where it is. PM is greater than P. If PM is greater than P, your system will accelerate or decelerate. Come on. This thing should be
Sir,
answered very
accelerate.
quickly.
Sir,
Accelerate.
sir,
All right. Very
because,
good. So, yeah, okay. No need to give the explanation because we already know these things. We have been discussing these things so far. Okay, so if your system accelerates, what happens to your delta or rotor angle? It increases or decreases?
so it increases.
Assuming there was no initial energy stored. So if there is no energy concept, it started from 0 point. Then if there is pure acceleration, my pure acceleration will shift my rotor angle to the right. So can I say, let's say we said that the fault will be cleared between a few milliseconds. So let's say during those milliseconds, your system came at delta 1. Can I say this thing? That my system will go from delta 0 to delta 1 during the fault. Can I say these things?
Yes, sir.
Is it okay?
Sir, can you
Yes,
repeat?
sir.
Okay, so let me repeat. So initially I was operating at point A, steady state operation, stable operation. Okay, then suddenly there was a fault. We know that during the fault, my power delivered to the infinite bus voltage will be 0. As such, we moved to point B. Still, let's say the fault is persistent. Our fault will persist for a few milliseconds. So first of all, it came from A to B. The fault is still there. At point B, we see that PM is greater than P. The fault is still there. So my system will accelerate. So if it accelerates, we know that delta will shift towards the right. The fault is still there. By the time the fault is cleared, my delta has moved from delta 0 to delta 1 at delta 1 instant, my fault is cleared. Have you understood up to this?
Yes, sir.
Okay. If the fault is cleared, definitely you will not remain at delta 1. I mean, at this particular point, let's say this is my point C. So from A, it has gone to B. From B, it has gone to C during fault. After the fault, that is when the fault is cleared, where will your system go from point C? Any idea? Try to
Sir,
think
it will
what will
come
happen.
back.
Bolo, bolo.
It will come back to A.
Unfortunately, it cannot come back to A like diagonally. Your answer is correct. At some stage, it will come back to A. That is fine. But can your system directly go from C to A?
No, sir. I think it will go from C to B first, then B to A.
How can it go from C to B? You are saying that my rotor angle will decrease. How can your rotor angle suddenly decrease? Try to think about this particular formula. This is what you need to use now, because your system has become exactly same as before fault. So now what will happen? This is the only crucial part. Rest of things, bolo.
ডে ওয়ান
Say.
থেকে মানে ওই পয়েন্টে পি কার্ভ যেটা ওইখানে চলে যাবে,
কোথায় কোথায় আবার বলো, সে अगेन।
পি কার্ভে চলে যাবে আবার, মানে লম্বা লম্বি পার্টিকেল যে পয়েন্ট আছে পি কার্ভে ডে ওয়ান।
Okay. So you're saying that it will go back to the PE curve vertically from which point? B or C?
সি।
C. Very good. Excellent answer. Yes, that is the correct answer. Okay. See, if I take a vertical point over here, let's give this point a name. Okay. We had an intersection. Let's say this is D, this is E. So my answer is your system will get back to E. Let's stop over here. How it is happening. So we know that my PE is P max sine of delta. Initially, when we were at point A, this was my PE naught. So sine was automatically delta naught. Now, when we are talking about after fault, then my PE will become P max sine, but now we see that this delta has become delta 1. So if it is delta 1, then this expression will take me at particular point E. So did we understand why it went back to E? Is it understood?
Yes, sir.
Okay. While this was happening, we said that my PM will be greater than P, so my system will accelerate. So whenever my system accelerates, some accelerating energy stored within the rotor, right? From our previous concepts, we know this thing. So which is my accelerating area now in this particular figure? Let's see who can say. So the question is, which is your accelerating area in this particular figure?
ADBC.
ACD.
ADBC. Any other opinion from apart from ADBC?
We can draw a horizontal line from E and then that intersection.
Okay, sir. If I draw a horizontal line from E, then that intersects PE. Okay, then continue.
And then the new area that will come from the intersection from the line with A.
That will be accelerating area. Is that so? What is the condition for that acceleration? Your PM should be greater than P. If you are going from E in any horizontal direction, then what is happening between PM and PE? Who is larger?
All right, P is larger.
Exactly. So if P is larger, you can have a deceleration area, but not accelerating area, right? So that means whatever
Yes, sir.
answer I got initially, that is the correct answer. You will have some accelerating area A, B, C, D. Okay. So we are clear up to point E. Now let's see what is happening at point E. Let's see what is happening now. So now what will happen to omega? What is the relationship between PM and PE? Again, at point E, tell me. What is the relationship? At point E, what is the relationship between PM and PE?
পিই বেটার দেন
PM is less than P. So if PM is less than P, then your system will accelerate or decelerate.
Decelerate.
It will decelerate. We know that thing. In the last class, the explanation I gave that from point E, my system will decelerate. That is, my omega will start decreasing. This will be point E. My omega will start decreasing, but my rotor angle at point E, it will have some inertia stored. Because of that kinetic inertia, it will shoot beyond E, right? This was the explanation, isn't it? The same conclusion can also be drawn using some equations, like what was your d del by dt? Can someone tell me what is d del by dt? Between omega and omega naught, there was some relationship, right? What is d del by dt with respect to omega? Wasn't it omega minus omega naught? Can you recall this relationship?
Yes, sir.
Yes.
Omega minus omega.
Okay.
Yes, sir.
Let's say initially my omega naught was 500. Let's say this was the stable operating point. Okay, just a second. I'm running. Yeah, sorry. So let's say this was omega naught. So when we accelerated, we know that during acceleration, my omega will be larger than omega naught. So let's say my omega suddenly increased all the way up to 500 during my ABC operation. Now, when we are coming at particular point E, my omega will start decreasing. We know that my omega will start decreasing. But can it go from 1500 to below 500 instantly? Can it do that?
No, sir, it cannot due to inertia
So-
and energy stored in the
Exactly. So it will slowly decrease. Let's say, first of all, omega will be somewhere between 1300. Still, if PM is greater than P, then slowly it will become 900 and it will keep on decreasing. So you see that while omega is decreasing, this relationship still gives you a positive result, right? Because your omega naught is fixed at 500, your omega from 1500, now it will start decreasing. So it will slowly become, say, 1300, then 900, but it will keep on decreasing. So that means this relationship will still give you a positive output. As such, your delta will increase. So if delta increases from point E, you will go to, say, some point F. We will explain how we can determine the point F. We will go to some point F, where this will be my delta max. But from point E towards point F, my omega will decrease. But from point E towards point F, my delta will increase. Are we clear up to this? Is it okay? Whatever I have said, come on. I need your answer. Yes, sir. No, sir. Repeat something you have to say.
yes, sir. Yeah.
Yes, sir.
Okay. Thank you. Okay. So now, how do we determine which will be my point F? The same question I asked in one of the previous classes as well. How can we determine what will be my point F? Any answer?
So there omega will be equal to omega naught.
Okay, when will that be? I mean, there is another criteria from where we can say when it will be equal. Your answer is correct. But when will that
So
scenario take place?
The decelerating area should be equal to accelerating.
Exactly, very good. So my decelerating area should be equal to my accelerating area. So can you tell me which is your decelerating area?
Sir, EFDG.
Right. So wherever my PM is less than my PE, that will be my decelerating area. So over here, this will be my decelerating area. Although in the figure it looks that decelerating area is larger, but I mean it is not drawn to a scale. So let's assume this is my A2 decelerating area. This is my accelerating area. So if my accelerating area will be equal to my decelerating area, at that point, we will assume that omega becomes equal to omega naught. Again, rest of the explanations are like previous class, that at particular point F, my omega is equal to omega naught, but however, my PE is still greater than PM. So my system will decelerate. So it will again start coming back. but it will shoot beyond E, it will go below A, it will go somewhere below A. Again, both of these should be equal at some particular point. Again, it will increase, it will go somewhere below F, again it will oscillate, and when there is damping present, your system will again stabilize at particular point A. If there is no damping, then your system will keep on oscillating, keeping A at its center. So the rest of the explanation is actually same as before. Any question until now? All right, so if you do not have any question, this is the figure that I had been explaining so far. The explanations are given, but again, I mean, whatever I have just said, it is very difficult to write everything on the slide. So maybe they are given in a little brief manner, but if you understand from the class, then it will be very simple. Okay, so what was the conclusion? If your system has damping present, it will finally it will be stable at particular point A. If there is no damping present, it will keep on oscillating, keeping A at its center. All these things are explained in these two particular slides. So any question until now, please, if you have any question, please ask any question. Okay, if there are no questions, now tell me something, then answer my questions. So what was the path that we assumed during fault? So during fault, we said it will go, okay, let me take the red color. During fault, we said that it will start from A, it will go towards B, then from B, it will go towards C, right? This was the path during fault. Do all of us agree? So we assumed that at point C, the fault is cleared. So we moved to point E. This was my complete path. So this point A was before fault, the entire was during fault, and this was after fault. Now tell me, let's say this fault was cleared in say 2 milliseconds, let's assume. Instead of 2 milliseconds, if the fault is cleared in 4 milliseconds, tell me what will happen.
Sir, it will cross
C will
del max.
shift-
It
sir,
will
C
cross
will
del
shift to
1.
the
Okay,
right.
fine. Yeah, right. It will shift more towards right. So that means the more time you take, your difference between delta 1 to delta 0 will keep on increasing. So if you go beyond this, what happens to your accelerating area? This is my initial accelerating area. So if you go beyond delta 1, what happens to your accelerating area? Increases or decreases?
Sir, increases.
Increases. So again, from the previous knowledge, let's say this is H. Can I say that my available decelerating area is EDHF? Can I say, I mean, this is my entire available decelerating area. So if I am taking more time, my accelerating area is increasing, and what is happening to my decelerating area?
So it is decreasing.
Decreasing. So in the same manner, I will have some critical point where my accelerating area will be equal to my decelerating area, right?
Yes, sir.
And that is that point is known as critical clearing angle. I mean, if the fault is cleared after the critical clearing angle, what will happen? Your system will become stable or unstable?
Can you repeat the question?
The question is, say I get at some point, say this is my del C, critical clearing angle. Okay, just a second. So let's say at say some point, I'm getting my del C where I can see that my entire accelerating area is equal to my decelerating area. And let's say that from going from del naught to del C, it takes 5 milliseconds, let's say. So if the fault is cleared at 6 millisecond or say 5.2 millisecond, then what will happen to your system?
Sir, system will be unstable.
Exactly, system will be
Unstable,
unstable
sir.
because my accelerating area will be larger than the available decelerating area, and as such my system will become unstable. So now my target will be to find this delta C, that is the critical clearing angle, just as previous example, I mean analysis that we had before. So again, this is let's say this is your accelerating area, So let's assume this accelerating area is equal to your decelerating area. Okay. So we apply EAC. You can understand all these things. Okay. So I'm not going to explain these equations. These are very, very simple equations. So you integrate, both the areas are equal. You do the integration. You get this expression. From here, you can see that PM delta C is positive over here. And PM delta C is positive, right? This is also positive. Okay, PM is, yeah, PM is there. Sorry, PM is not vanished. Everything is there. Yes, PM is there. P3 max is there. Delta max. Okay, fine. Yeah, you can finally come up to this expression. Just take some common, do left hand side, right hand side. I mean, you can. Is it okay if I'm going fast in these things? I mean, can you do that? Can you go through these expressions? Or do I need to explain? Explain korbo? Should I show how we are going from this line to this line or from here to here? Do I need to explain?
So what is P3 max?
What is?
P3 max, what does it mean by 3?
P3 max means after fault, power after fault. If I go back a little bit over here, you can see that you have got your P3 max, right?
Yeah, yes, sir.
So P3 max and PE1 max are same thing. Okay, that is after fault. Sorry. Yeah. Okay. Anything else? Anything else you want me to explain? Come on, you can ask. Okay. So if you do not have any questions, so come on, if you have any question, you have to ask. Okay. Otherwise, these equations are really, really simple. Simple 1, 2 lines, taking common, canceling the common terms, all these things. Okay. So that's why I'm not showing you. Okay. So finally, we get del C. So if you get del C, you can see that it is in cos del C. So your del C can be written as cos inverse. Then whatever is there over here. So you can just plug this value over here and you will get the value of your del C, which is your critical clearing angle. Okay. Is it okay? Any question until this? Okay. Then what is our target is we are interested in finding the time actually. Okay. We know that fine. Delta C, a critical clearing angle in rotor, that is fine. But sensing the rotor angle is a bit more complicated than calculating the time. Calculating the time is much simpler. So with del C, if we can find some time which corresponds to critical clearing time, then it becomes very easy for us to operate the relays. Like we can set the relays that you can wait until this amount of time. But after this or before this, if the fault is not cleared, then just disconnect the generator or just switch on the relays. Okay. So for that, we are interested in finding the explicit time TC from this information delta C. So let's see how we can do that. This is quite easy actually. So this is our swing equation. We all know that. So typically swing equation is over here PM minus PE. So we know that during fault, my PE becomes 0. So this one becomes 0. As such, we get this expression, that is H by pi F naught d square del by dt square is equal to PM minus 0. So from here, if you take H by pi F naught on the right hand side, then you end up getting this equation. Clear up till this? So now you can go for your integration. So if you integrate it once, then one of the differentiation goes away. So it becomes d del by dt. We are integrating with respect to t. On the right hand side, there is no term containing t. So we go for integration of a constant. You can place 1 over here. Okay. So same thing. So if you place 1, if you integrate from 0 to t, just plug in the values, you will get t by h. If you go for second integration, so from 0 to t, our angle will be from del 0 to del max actually. So this will be not del, it will be del max minus del 0 because we are looking for the maximum point, right? So this will be this differentiation. If you integrate and plug in the values, it will be del max minus del. On the right hand side, this t is still there. So if you integrate, it will be t square. So you will end up getting pi f naught PM t square by twice h. So if you just take the root and take del max minus del naught on the right hand side, you will end up getting this expression. Is it okay? Yes, no, something.
Yes, sir.
There was only one assumption, that is my PE was taken 0 during the fault. From their simple integration, plugging in the values, then changing the size. That's it. So now you look at this TC, your H is constant. You need to know your clearing angle from the previous slide. So from here, you will have your clearing angle. So you will know your clearing angle. You will always know your initial operating angle. Pi is fixed, F naught is fixed, PM is fixed. And thus you can calculate your critical clearing angle. So your target should be your circuit breakers should operate before TC. It cannot reach TC. Say for some reason you are getting your TC is 5 milliseconds. So what you have to do is your circuit breakers should operate before 5 milliseconds, maybe at 4.9 millisecond or 4.8 millisecond is fine, but not after 5 millisecond, because if you touch 5 millisecond at 5.01 millisecond, if the fault is not cleared, your system will become completely unstable. So you need to make sure that your circuit breakers are separating your generators before this clearing time. Okay, so it's been 1 hour. Any question? Okay, so good thing is you will have a record of this lecture. So this was the second application. The third application is what will happen if we have a fault in between. Okay, so this I will start in the next class, not in this class. So all these things we discussed today was what will happen if you have a fault at one end of one of the transmission line, and we applied our equal area criteria, and we saw that we can find the critical clearing angle, then corresponding we can find the critical clearing time, and my objective is that my critical clearing time is considered in such a way that my circuit breaker should work before that critical clearing time. So is it okay, everyone? Okay,
Yes,
so
sir.
if you do not have any question, I can stop sharing. Okay, let me pause the recording. Just a few more words, then we'll finish.